So, in the next part of the course, we will look into another important testing challenge, which is known as the testing of memory. So, testing of memory is significantly different from the testing of logic circuits consisting of say this logic gates, because memory has got some regular pattern and the structure is regular in nature. It has got a particular architecture consisting of the decoder, then sense amplifiers and all that. So, that is one thing, and that is one side. The other side is that it has got a number of cells. Okay. So, the data are stored in the cells, and the cells they show different types of behavior. Like it may be the case that when the cells being in close proximity of each other, when we try to put a particular cell to some value, some neighboring cell also changes their value. So, that was not the case in case of in the logic circuit, because we could we have always assumed that until and unless there is a bridging fault. So, these lines can be changed without any problem, but that may not be the case in case of in the memory. And also the fault models are totally different when we are looking into this memory testing. So, that way it makes a very interesting part of this testing VLSI testing process. So, typical memory production flow or the RAM production flow is the is like this. First we start with the wafer. At the wafer level we do a full probe test, and then if there is some defects are found, so we do some laser repairing, so something that is corrected locally, and then it goes to packaging. So, in the packaging, after packaging, so it we do some tests again, which is known as pre-burn-in test, pre-BI test. So, so there some basically some patterns will be written and it will be read back, and we see that whether they have been done properly or not. Then it goes into the burn-in phase, where it is subjected to a long test sequence and doing for maybe different types of patterns and all that. And then so some chips they will survive in the burn-in phase, they will go to the post BI, post burn-in test. So, again after the burn-in phase, some more test will be done. So, then the marking will be done, like which one is good, which one is bad. Then the final test will be done, visual inspection, quality assurance sample test, and then shipping. So, this is the total RAM production flow. Offline testing of RAM, so it is done in this way, that is parametric testing, the DC and AC. So, we can measure some of the voltage values, some of the current values that are there. So, that way we can do some parametric testing of these various points. Then it goes into reliability screening. So, this is another offline testing. So, long cycle testing. So, we made say large number of read write operation and see whether whether the values have been written properly or read properly or not. Then burn in. So, this can be static or it can be dynamic burn in. So, under the it may be dynamic means it is put into system operation, and the static means it is not in the it is statically tested. So, before it is putting into this functional test. So, it is we do some testing, so that we get some confidence about its operation. Then the functional testing. So, device characterization. So, we try to see what sort of failures are occurring, and if the failures are found, then we try to model like why this failure has occurred, and that way we can do some device characterization, some fault modeling. So, whether it is we can model some of the faults, like there may be actual defect may be something different, but it may be modeled as some other fault. So, this that is true for logic faults also. So, that same thing here. So, we have to do some sort of fault modeling, and then there are some test generation algorithms. So, that are run for the functional test purpose. So, we start we start with the device characterization, then we do some fault modeling, and then finally, some test algorithm is run to generate test sets. So, these test sets, some small number of test patterns are generated which act as background. So, you see that there is an array of cells in a memory. So, they need to be put to some initial values for testing. So, that is actually the background pattern. So, under a background, so we can go for applying some more test pattern, so that we can get some high fault coverage and the test time is also less. So, this background initialization becomes an important part of the testing RAM testing part. So, DRAM functional model. So, how does a DRAM memory looks like? Okay. So, you see that we have got a memory cell array. So, this is the memory cell, the array of memory cells where actually the data are going to be stored. Now, there is and so the address part that comes. So, address part is divided into two parts. So, address the row address and column address. So, address part, the address that is coming. So, it gets latched onto this address latch, and then this address is divided into row part and column part. They go into row decoder and column decoder, and this row decoder will select a particular row, column decoder selects a particular column, and that way the content of that cell is read. And what happens is that this in the DRAM cell. So, there are this is basically nothing but a single capacitor, and that single capacitor gets charged when we store a particular value there. And when we try to read the content of that cell, so there are two lines, one is known as bit line, another is known as bit bar line. So, the logic that we get at bit line and bit bar line, so their difference will tell us what is the value that was stored in the cell. So, there is a sense amplifier that will identify that will amplify the difference between this bit and bit bar lines, and this difference gets amplified and stored into the data register. So, if for the read operation, so this difference between this bit and bit bar line is coming to the data register, and that is coming as data out from the memory. On the other hand, if it is a write operation, then this data that is there in the data register, so that is put into this write driver. Again, this address location, the address decoders, the row and column address decoders, they select a particular cell, and accordingly the value gets written onto that cell by again through that bit and bit bar lines. And also, since this is a DRAM, so we need to have some refresh logic. So, refresh logic, it selects, it goes to the column decoder, and this column decoder will decode the value, will decode that particular column, and for each entry in that column, so it will get rewritten. So, this value comes to the data register, from data register it goes to the write driver, and from write driver the cell is again rewritten. So, that refresh cycle is also a part of this DRAM functional input. So, we have got this data flow and control flow controlling the whole operation of this DRAM. So, this is the so functional. So, this may be a typical example. So, we have got this total 18 bit address. Out of that, this row may be row bit may be 10, and this column address may be 8. So, they go to two different decoders. So, the memory cell is the memory array is 1 megabit memory. It is arranged as 1024 by 256 bits. So, each row has got 1024 bits, and each column having 256. So, there are 1024 rows, and each of them having 256 bits there. And we have got sense amplifiers for at every column. So, that the bit and bit bar lines are amplified, the difference between them, and that way these values will be stored in the data register for read operation, in the data out register, and for data in register. So, they will be for writing onto it, the value will be written onto this data in register, and from there they will go into this memory cell. Now, there are timing controls. So, that controls this read access, this refresh control, and all these are controlled by this timing. So, that will activate different modules within this DRAM. Now, the functional fault models that we have for RAM, so that is significantly different from the classical fault models that we have for logic circuits. So, classical fault models are not sufficient to represent all important failure modes in RAM. Sequential ATPG is not possible for RAM, because it is a huge number of cells. So, if you try to do sequential ATPG, so if we model every cell as a flip flop or latch, so that way it is a huge number of flip flops. So, it is not possible. Functional fault models are commonly used for memories. So, normally we go for a functional fault model. So, they define the behavior of the faulty memories. So, faulty memory like two cells getting same value coupled to each other. then some cell value, some cell reaching a particular continually holding a particular logic level. So, like that stackered fault, is some sort of stackered fault will be there, but there are some other type of coupling faults that will come into picture. So, we will see them. So, new fault models are being proposed to cover new defects and failures in modern memories. So, with the new strategies for new technologies coming up for designing these memories, so that the defect possibilities are also changing. As a result, the technology for the testing process, the fault models for them, that they are also changing. So, anyway, so these are functional fault models are going on. The first, so we will first consider the static RAM fault model, which is known, so we will look into two such fault models. One is stackered fault model, another is transition fault model. So, stackered fault model means a particular cell is stuck at 0 or stuck at 1. So, this is similar to the stackered fault that we have in logic circuits. So, stackered fault occurs when the value of a cell or a line is always 0, that is a stuck at 0 fault, or always 1, a stuck at 1 fault. A test that detects all stackered fault guarantees that from each cell a 0 and a 1 must be read. So, if we are generating a set of test pattern that can detect all stackered faults, then for every cell it must be reading a 0 and must be reading a 1. So, that test patterns must be ensuring that. Then there is a transition fault. So, transition fault, the cell fails to transit from 0 to 1 or 1 to 0 in specified time period. So, we apply a transition on the cell and see whether that transition has occurred in that cell, the cell content is changed or not. So, maybe we write a 0 value, then we try to see whether after some time whether the 0 value has been written there or not. Similarly, previously the cell content has to be ensured to 1, of course. Then similarly, if we are going to check for a transition from 0 to 1, so initially we write a 0 there and then try to write a 1 and then try to see whether this value has 1 has really come onto the cell or not. So, that way we can have transition fault. So, cell fails to transit from 0 to 1 or 1 to 0 in specified time period. A cell has a transition fault if it fails to transit from 0 to 1. So, this is written as rising stuck at 0. So, rising and 0 and 1 to 0 falling, and previously the pattern was 1. So, previously the bit was 0, now it is trying to rise, and here it means that previously the bit was 1 and now it is trying to fall. Another major source of failure of RAM is the address decoder. So, you see that in this RAM we have got this address decoder. So, if this address decoders fail, then we are not going to check the particular memory cell, but something else. So, if the address decoders fail, then also we have got severe problem with the operation of this memory. So, this address decoder faults, so they formulate one class of faults for this RAM. An address decoder fault is a functional fault in the address decoder that results in one of the 4 kinds of abnormal behavior. First of all, given a certain address, no cell will be accessed. So, we put a address, but none of the cells get selected. So, that is a problem with the address decoder. A certain cell is never accessed by any address. So, we try to select one particular cell, but whatever address we put, so it is never selected. So, that is there is a decoding problem. So, the difficulty is that you see from the address decoder, so every cell has to be selected. So, that way the address decoder assumes a very important part, a very important role in the operation of the memory. The third type of fault that can come is given a certain address, multiple cells are accessed. So, several cells are getting selected simultaneously. So, that is also an address decoder fault. A certain cell can be accessed by multiple addresses. Multiple addresses they select same address location, same cell location. So, that is also type of fault. So, the address decoder we can have these 4 types of faults. Then we can have something called a stuck open fault. So, it occurs when the cell cannot be accessed due to a broken word line. Okay. So, the cell has become unaccessible. So, we cannot change the content of it. So, that is the word line failure is there. A read to this cell will produce the previously read value. So, whatever was previously read, so it will again give the same value, though we try to change it and then read it. So, this change will not get reflected into the red value. Then more interestingly, in RAM we have got the coupling fault. So, these are specific for these memories. So, a coupling fault between two cells occurs when the logic value of a cell is influenced by the content of or operation on another cell. So, you see that the content of a cell is 0. So, that affects content of one of its neighbor. So, that is one type of coupling. Similarly, I want to make a transition on a particular cell that affects one of its neighbor. So, that is also a coupling fault. So, we have got this state coupling fault. So, coupled cell is forced to 0 or 1 if coupling cell is in the given state. So, we coupled cell is the victim cell and the coupling cell is the aggressor cell. So, we are trying to put a 0 in the aggressor and the victim is also getting a 0, or we are trying to put a 1 in the aggressor, the victim is also getting 0. So, this is called state coupling fault or CFST. Then there is inversion coupling fault. It is a transition in coupling cell complements the coupled cell. So, there is a transition, the coupling cell makes a transition from 0 to 1 or 1 to 0, and as a result the victim cell gets inverted. Okay. So, that is the transition fault, the inversion coupling fault or CFIN. And we have got idempotent coupling fault. So, a coupled cell is forced to 0 or 1 by coupling cell if the coupling cell transits from 0 to 1 or 1 to 0. So, this is whenever this coupled cell is going from it goes to 0, if the coupling cell changes from 0 to 1, it goes to 0. Similarly, if it goes to 1, if the coupling cell changes from 1 to 0. So, if this thing happen, we call it an idempotent coupling fault or CFID. So, these are the different types of coupling faults that have been observed in the RAM cells. We can have intra-word fault and inter-word this coupling fault. So, the intra-word coupling fault means within a particular row we have got coupling. So, this cell and this cell, so they are coupled. So, if this cell content goes to change, so this cell is also getting modified. And we have got inter-word coupling, maybe we have got two successive words, and say this word when it is this particular bit when it is changing, it affects this cell of the next word. So, we have got inter-word coupling. So, we have got intra-word coupling as well as inter-word coupling. More fault like the disturb faults, the DF. So, DF, the victim cell is forced to 0 or 1 if we read or write aggressor cell, and maybe the aggressor we do it successively, we do it continually. So, if we read or write an aggressor cell continually, then it permanently the victim cell is becoming 0 or victim cell is becoming 1. So, this victim cell and aggressor cell may be the same cell also, but what is happening is for a particular cell we are continually doing a read or write operation. As a result, that cell or some other particular cell, so that becomes 0 or 1. So, that is a disturb fault, that is marked as disturb fault, and it is detected by one test which is known as hammer test. So, we will not go into the detail, but because that is quite long. And then there is read disturb fault. So, there is a read disturb fault if the cell value will flip when being read successively. So, read disturb. So, we are just trying to read the content of the cell. So, when we read the content, read a cell, so its content should not be disturbed, its content should not be modified. So, this read disturb fault says that if I am reading it continually, then the content of the cell gets flipped. So, that is the read disturb fault. Then there is data retention fault. So, data retention fault basically for SRAM. So, we have got leakage because SRAM there is no refreshing. So, there the back to back inverters are connected to form the SRAM cell. Now, this or maybe there are some other designs are also available, but essentially what happens is that ultimately this bit that we are going to store is stored by means of some feedback mechanism between transistors. So, they are actually holding the value. So, now due to leakage, so these transistors may lose the logic level. So, that is the static data loss. So, that is the leakage fault for SRAM. for this DRAM. So, we have got the refresh fault and leakage fault. The refresh circuit is trying to do the refreshing of this RAM cells continually by reading the value from the cell and writing it back onto there. But if there is some problem in that refresh circuitry itself, then this refreshing will not work. So, that gives rise to the refresh fault, the content of several cells may be lost. Similarly, we have got the leakage fault for DRAM cell as well. So, that is the leakage fault for DRAM. So, if we look into the complexities of this test pattern, so if the time, so if the size of the memory is 1 million, 1 mega, 16 mega, 64 mega up to say 16 gigabit like that, and if I have got a test generated test policy that that can test the memory in linear time, then and the test runs at 100 megahertz frequency and it can do the testing in linear time, then for 1 megabit size memory, so it takes 0.01 second, whereas for 16 gigabit size memory it takes 2.8 minute. On the other hand, if the complexity of this testing process is high, so it requires say 10 n time to apply the test pattern and see the responses, then this is 0.1 second and this is 28 minute. So, that is, you can understand now the complexity has started growing. On the if the complexity of this test application process is n log n, then where n being the number of cells that we have in the memory, it is n log n, then this 16 GB memory, so it will require 1.6 hours to test, and if the complexity is even higher, n power 1.5, then it requires 255 days to test 116 GB memory, 16 gigabit memory, and if the complexity is n square, then it will require 915 centuries to test this 16 gigabit memory. So, there actually is the complexity. So, the normally when we are designing any policy or any algorithm for some problem, so we are normally happy if it does not go into the exponential domain. So, if it is remaining in the polynomial domain n square, n log n, n cube, so like that we are happy because we know that it is not going to affect much in terms of time. However, here you see you cannot think of anything, any algorithm which is beyond the linear time, because if you go beyond linear time, then these memory capacities are increasing every day. So, with these new technologies are coming, so these memory capacities are increasing say every day. So, this way the testing time will of those memory chips that will become more and more high. So, we cannot, I do not think we can afford say 1.6 hours to test 116 gigabit memory for its current operation. So, any of these computers now they have 16 gigabit 16 gigabyte also in that range. So, that way the amount of memory available on these normal systems are also very high. So, if we are going to test them, we cannot go for this highly complex test pattern sets, highly complex test application procedure. So, the testing process for memory should be simple, it should be fast, and at the same time we want that all the fault models that we have discussed. So, all those fault models will be covered by the tests that we are applying for the memory. So, a test algorithm or simply a test, it is a finite sequence of test elements. So, how do you, so we have to apply a sequence of test element. A test element, it contains a number of memory operations. So, what is a memory operation? We may like to read the content of the memory cell, we may like to write some value onto the memory cell, maybe we write some value and then after some time we try to check the content. So, that way we can see, we can try to see whether this operation was successful or not. So, a test algorithm, it is a finite sequence of test elements, and a test element, it contains a number of memory operations or the access commands, the read write access commands. So, there may be we may perform some data pattern background or data pattern or background specified for the read or write operation. So, first we have to set the memory to some background and then we try to do a different type of write. Then also we need to tell the address sequence in which the read write operations will be done. So, first we write at a location, then at the next location, then at, so is it in an increasing order starting from the lowest possible address to the highest possible address, or it is in the decreasing order. So, maybe we first write it in the increasing order, and then while reading we read it in the decreasing order, so that we get certain types of faults detected. So, that way we can we will see that this type of read write address sequence, that also has got some definite role to play in detecting faults. So, this main memory test algorithms, so they are known as march test algorithm, because they define some sort of marching pattern through the memory. So, this march test algorithm, that is also a finite sequence of march elements, just like any test algorithm is a sequence of test elements. So, march test algorithm is also a sequence of march element. Again, a march element is specified by an address order and a finite number of read write operations. So, each element will tell me in which order you are going to apply the you are going to do the read write operations, and the second it will tell what are the read write operations that we are talking about. While talking about say march test, so this is the thing, that is we can apply this symbol. So, this is the address sequence is in ascending order, that is starting with the lowest possible address. So, it will go upwards. Then there is a decrease. So, this if this symbol is given, so that is address changing in the descending order. So, this symbol tells that okay, you can put the address in either of these two orders, ascending or descending. Then as far as the operations are concerned, so there are two operations, R and W, read operation and write operation. So, when you are trying to read some value, so you have some expectation. So, maybe previously I have written a 0 there. So, I would expect that I will read a 0 if the cell content is remaining intact. So, while talking about the read operation, we tell that I want to do a read, and what is the expected value that I am getting that I like to have from the cell. So, R0 is that I am expecting to read a 0 value. Similarly, R1 means we are expecting to read a 1 value from the cell. Similarly, the write operation W, so it means that we want to writing 0, so that is W0. So, we want to write a 0 value into the cell, and W1 means we want to write a 1 value into the cell. An example of a march sequence may be like this. So, sorry, this is not the C, actually this is the problem of this PowerPoint. So, this particular symbol should be there. So, it tells that first we apply this write 0 in any order. So, upward, downward, it does not matter. So, this is the first march element. So, for all the cells we are writing 0. So, maybe in an if we follow an upward addressing, so it is for all the addresses or for all the locations it has written as 0. Now, we would like to check whether this 0 has been written properly in all the cells or not. So, we do this operation for all the cells, we first read the content of the cell and we are expecting to get a 0 there, and then after that we are writing a 1. So, we check the value rate from the cell, and then we write a value 1 at that point. So, we are complementing the content of that cell. Then in the descending order we are doing this read operation. So, since we have written a 1 here, so we are expecting to get a 1 while we are reading. So, this is the descending order reading, and then we are writing a 0 there. So, if the memory is flawless, then what will happen? Initially the memory content will be all 0, then I will be reading the 0 and writing 1 there. Then at the end I will be reading then on the reverse order I will be reading this one and writing the zeros there. So, that way I will be getting the again the memory back to all 0 content, but it will be testing a number of faults that we will see in the successive lectures.